Hi everyone, my name is Yanfeng Li and my project is about deep learning for individual clan size regression. So why this topic is important? Firstly, insurers need to accurately estimate outstanding claim to prepare adequate reserve. However, the traditional GLM approach tends to be manually intensive and can be heavily based on subjective judgment. And this project explored the application of deep learning to individual reserving. So deep learning shows success in various actual applications, and this project will explore various techniques in deep learning. So in this project, I used the Australian automobile bodily injury claims dataset, which contains around 20,000 claims in a decade. So the dataset contains claim development information, injury information about the severity of injury, the legal information, and finally, our target variable is the aggregate amount of claim payment for each claims. Note that some values in injury type 2 to 5 and NA, which indicates that the corresponding claims only has one person injured. So the dataset and claims and the categorical features are processed using the ordinal encoding before feeding into the networks. So in the next session, I will present the network architectures explored in these projects. So firstly, this project explores a standard feed-forward neural network with embedding layers. So as shown in diagram 1, the categorical features are entered into the embedding layers. The embedded features will be then combined with the numeric features in the concatenate layer before feeding towards the hidden layers. So the number of neurons used in each hidden layers will be 40, 30, and 10 with the radial activation function, which is inspired by the Gabrieli's work. So although the number of neurons and the hidden layers are fixed, the learning rate and the number of epochs will be tuned to optimize the ensemble's performance, and several regularization techniques will be explored to mitigate overfitting. So the second network architecture being explored is the combined actual neural networks, or CAN. So we denote f as the regression function for the GLM with parameter beta and input space x, and g as the regression function for the neural network with weights w and a depth d. So then the regression function of CAN can be specified in equation 3 with parameters beta and w's. So this idea is also illustrated in diagram 2. So for implementation, we can use a skip connection to add the GLM predictions to the output layers. So in the next session, I will present the empirical results. So recall that this project explored the regularization techniques of L1, L2, and the dropout layers. So firstly, a grid of penalty rates and learning rates is defined. So for each technique, all possible combinations of learning rates and penalty rates are tested. And the combinations that use the smallest validation IMC will be chosen. The red rectangle highlights the best combination of learning rate and penalty rate for each regularized network. The same procedure is repeated for CAN, which is shown in paper. So table 1a shows the validation IMC for each model after tuning. So all networks, except for the L1 regularized networks, outperforms the benchmark GLM. So the neural net with dropout layer has the lowest validation IMC, and so it is selected. So table 1b summarizes the test IMC. Our selected model still outperforms the benchmark GLM. Although it slightly outperforms the L2 regularized network, the difference tends to be small. So up to now, we can see that the selected network outperforms the benchmark, which is great. But can we make these results more robust and stable? So the answer is yes, by using a neural network ensemble. So this idea is by the ensemble learning methods. So for a given neural network structure, it is fitted on the training dataset k times with differences to obtain a total of k components models and the corresponding k predictions. The ensemble predictor can be then specified as the average of individual predictor. So figure 1 shows the distribution of training and validation IMC for neural net and CAN over 40 calibrations with differences. So as we can see from the figure, both the training loss and the validation loss are quite volatile. For instance, if we are in bad luck in setting Cs, we can end up with a high loss when making predictions. The blue lines and orange lines mark the IMC of the NA and the CAN ensembles. As per the figure, both ensembles use a lower IMC than the majority of individual networks. The outstanding performance of ensembles may be explained by its capability to reduce the prediction variance, which will improve the generalization performance. Additionally, component models can compensate each other when making predictions. As a quote from Goodfellow, different models will usually not make the same mistake on the same data. So as a final comparison, the neural networks ensemble has the best performance on both the validation and test sets among all the models. So as a quick summary, this project has explored two network architectures, and the selected model outperforms the benchmark GLM on both the validation and the test set. Additionally, this project has found that using an ensemble of networks can further boost the network's performance by stabilizing the prediction. And here is the appendix and the reference for this project. Thank you.